Hi, welcome to ESI 412, Nanotechnology, Materials, Infrastructure, and Safety. I'm Professor Ukjun Nam at the Pennsylvania State University. We're going to talk about colloid and then colloidal chemistry. And then we also will talk about the vapor, liquid, solid approach. And then we will talk about the way of people are doing to integrate this kind of nano element to the actual application. So colloids and colloidal chemistry. So what is the colloid? The colloid is some kind of a subdivision of material which is mixed with some of the mediums. So those kind of a subdivision materials size is between 1 nanometer to about 1 micrometer. So the properties of colloid is it is not dissolved into the medium. So it is kind of a separate material, but it is kind of a smaller than those kind of medium, but it is kind of technically mixed with those kind of medium, but it is kind of present as an independent material. So the colloidal suspends like very stable dispersions, and then one of the good example is gold nanoparticles suspended in the aqueous solution. So depends on the size of the gold nanoparticle. Those kind of color of the solutions are very different from very clear to the very dark red. So this is the kind of an example. So in the medium, those kind of colloidals kind of suspended like this. And then in this case of that, this kind of size of the colloid is so small, the surface effect is dominate than volume effect. So that is why those kind of a small colloid is not affected by the gravity. So that is why it can be dispersed in that medium. So this kind of a colloid has its unique kind of properties. So it has unique properties for the light scattering, and then those kind of colloid are present in the mediums like with a Brownian motion. And then this can be charged or this can be moved by some kind of outside of the force. So this is the example of the colloid. So the aerosol is the medium is on gas, and then the gas is dispersed in the liquid medium, and then soror paste is the colloidal is a liquid, and then the medium is a solid. So this is the whole different kind of a combination between the colloid and then the medium, and then this is the example. So the way of creating this colloid, there are two ways. One is a condensation, and the other one is an dispersion method. So this one is basically synthesize those kind of colloidal materials. I will show you the videos in couple slides later. And then the other method is from the big chunk of the materials, we make those kind of structures, those kind of small nanoparticle structures out of the big chunk of the materials. So once we make those kind of nanocolloidal structures, we can just filtering all those kind of things using this kind of way. So basically, for the synthesis of the gold nanoparticles, this is an condensation method. So it is basically the chemical reaction. So we have precursors, and then as we just add some chemicals work as a reducer, this kind of ions, source ions, just oversaturated, supersaturated, and then make a nucleation, and then as time goes on, those kind of size of the nanoparticles are getting bigger and bigger. So this is the another kind of a view graphs showing that. So as you add the reducer to the precursor solution, those kind of atoms aggregated, and at some point it just makes some nuclei which consist of the around 11 gold atoms. From this point, once those kind of nuclear is kind of formed, the embryo is formed, from this point those kind of nanoparticles are getting bigger and bigger as time goes on. So this is the video actually showing that gold nanoparticle formation. So this demonstration shows two methods. So initial phase actually is just this is the in these stages we just putting those kind of gold solutions, and then this is the reducer, and then as we put the reducer we see some color changes, and after mixing those solutions, as we just put these kind of mixed solutions into the hot plate at certain temperature, those kind of a color change, actually this video did not show the kind of more detailed processes, but the color is kind of getting darker and darker as time goes on. So we can assume those kind of diameter of the golden nanoparticles based on this color, but this video goes one step further. That one is at this point, those kind of golden nanoparticle, the surface is gold. So this kind of golden nanoparticle just maintaining its kind of equilibrium distance by the surface charges of the gold. But once those kind of equilibrium of the medium is broken by the changing the pH or putting some kind of a contaminant in there, those kind of dispersed gold nanoparticles just to quickly aggregate, and then just to those color of the nanoparticle solutions becomes clear, and then you will see those kind of agglomerated gold nanoparticles on the bottom of the bottle, which is black in color. But so from this point, the reason why this video added acetone and hexane and dodecaine thiol and as we are waiting for that, this one makes phase separation, and then you can see the top solution is kind of red, and then the bottom solution is kind of clear. So what happened is at the before we add that acetone, hexane, and then dodecaine thiol, the gold nanoparticles are present something like this, and then the surface of the particle is on gold. So dodecaine thiol is an this kind of a molecule. So what this one has an SH as a ligand molecule, and then it has 12 carbons, and then these carbons all having a hydrogen bond in each of them. So basically adding those kind of acetone and then hexane and then dodecaine thiol just to make one monolayer of this kind of carbon hydrogen polymer layers coated the surface of the gold nanoparticle. So in this case of that, even we can dry the medium. So we can dry the aqueous solution, and then when we as we dry that medium, this one is on powder form. When we needed to make those kind of a colloidal solution again, for this case, we can just simply add the medium again, and then if we shake well, these kind of nanoparticles just be dispersed in the medium, and then it can just coming back to the its original form. In this case, once these nanoparticles aggregated, no matter we remove the medium or not, we never be able to make these nanoparticles dispersed again. So to make those particles to be redispersed, some people are normally putting this kind of a monolayer of the self-assembled monolayer on top of the gold. So in this case of that, those kind of nanoparticle solution is much more stable in state. So this is another way we can make those kind of nano particles. So in this way, we are not synthesizing those kind of nanoparticles, but as you can see from the videos, the starting material is a gold bar. So actually, this kind of red smoke is an gold nanoparticles produced by the laser application. So you may see some of the bright red spot around this surface of the gold bar applied from the outside. So those kind of high energetic lasers just making this kind of gold nanoparticles. So this is the lasers. So using this way, we can also make this kind of gold nanoparticles out of the big chunk of the gold bar. And this is another kind of colloidal solution. So right now, this is an cadmium selenide nanoparticle. The way of synthesize this semiconductor nanoparticle is the same as the gold nanoparticle. So we'll see how they are making it.
It's an extremely simple tool, but also extremely pointy.
Warning: this experiment uses toxic and carcinogenic reagents and directly handles extremely small inerts. In this video, we're going to make cadmium selenide quantum dots, a type of nanoparticle with interesting properties. First, we need to make our source of selenium. Get 30 milligrams of pure selenium powder and add to it a stir bar. Then add in 5 milliliters of 1-octadecene and turn on the stirring. Now add 0.4 milliliters of trioctylphosphine. Keep stirring and gently heat it until all the selenium dissolves into a clear liquid. What's happening is the trioctylphosphine is reacting with the selenium to form trioctylphosphine selenide. Once it's ready, seal it and let it cool. This will provide us with about 5 experiments worth. Now get 13 milligrams of cadmium oxide in a flask and place in a glass thermometer. Mine happens to be a glass encapsulated digital thermometer. Now add to it 0.6 milliliters of oleic acid and 10 milliliters of 1-octadecene. Now heat the mixture until the cadmium oxide completely dissolves. What's happening is the cadmium oxide is reacting with the oleic acid to form cadmium oleate. After the cadmium oxide dissolves, keep heating until the mixture hits 225 Celsius. While you wait, get everything set up. Have a dozen or so small vials or test tubes and prepare a syringe with 1 milliliter of the trioctylphosphine selenide solution from before. Be ready, because you need to work quickly.
So this is the chemicals work as a reducer, but what I wanted to remind you is that when we talked about those kind of nanotechnology, you may remember, based on the size of those kind of nanoparticles, those kind of color of the nanoparticle is kind of different because of those kind of quantum confinement effect. Actually, this cadmium selenide quantum dot can produce cover all those kind of visual light. So as you will see during these videos, actually the video will take some portion of the solutions from the initial as soon as this kind of a reducer is added to the chemicals. So at this point, those kind of nanoparticles did not formed. So from the first take out, the size of the particles are getting bigger and bigger, and then it just shows different kind of colors.
Once the cadmium solution reaches 225 Celsius, inject the selenium solution and give it a quick shake. Now immediately start withdrawing small samples of the solution, about half a milliliter to a full milliliter, and put them into the vials. For the first several samples, try to do this one after another as fast as possible. Then withdraw only when you see the color significantly change. What's happening is the cadmium oleate is reacting with the trioctylphosphine selenide to form cadmium selenide. These particles start small but grow in size along with the solution reacts. Now this growth only continues if the temperature is maintained, so withdrawing it at regular intervals and placing it in a room temperature vial stops the reaction and locks the particles into their current size. So by controlling how long they stay in hot solution, We can control their size. The oleic acid surrounds or caps the particles and keeps them from aggregating. Okay, now we've made quantum dots. These particular quantum dots are fluorescent in the visible region, and if exposed to an ultraviolet light will fluoresce different colors. Now scientifically, we have to ask the question, if all the samples have exactly the same chemical composition, why do they have different colors? The difference arises because the particles are so small that the allowed quantum states of the electrons in them are partially determined by the particles' shape and size, not just on their composition like in bulk materials. The best analogy I can think of actually is a stereo system. Large speakers are really good at producing long wavelength, low frequency bass sounds, while smaller speakers are really good at short wavelength, higher frequency sounds. This is due to differences in the size of the diaphragm and the frequencies it can support. Likewise, for quantum dots, the smaller the dot, the smaller and bluer the natural wavelength of light it will emit. The bigger the dot, the longer and redder the light it will emit. Quantum dots are being researched because there are many applications, such as making solar cells more efficient, better display technologies, and even medical imaging applications. So even if you can't make them in the lab, I'm very sure you'll soon encounter them in your daily life. Thanks for watching. Please subscribe, like, and comment.
So the way of synthesize this kind of a semi-conductor quantum dot is kind of very similar to those kind of a metal quantum dot. So we will see there is an organic version of the quantum dot available. The way of making those kind of organic quantum dot is kind of a little bit different, but this kind of organic quantum dot is used for drug delivery. So we will watch how people are making that quantum dot. Actually, there are two parts of the video. So this first video just shows more about the liposome itself, liposome basics, and then the second video shows how people are making those kind of liposome quantum dot. So I will skip the first video. So but I recommend you to watch this video later.
Encapsula Nanosciences presents Liposome Basics Part 2. Here we describe the basic methods for preparing and sizing liposomes. The simplest method for preparing liposomes is hydration of dry lipid. The lipid is dissolved in organic solvent along with any lipid-soluble compounds to be incorporated into the liposomes. The solvent is commonly removed by rotary evaporation, resulting in a thin film of dry lipid. Some solvents can be removed by lyophilization, resulting in a dried lipid cake. An aqueous solution containing water-soluble compounds to be encapsulated is then added to the lipid film or cake to hydrate the lipid and form the liposomes. The aqueous suspension must be heated above the phase transition of the lipids in order for the liposomes to form. The resulting multilamellar liposomes consist of many concentric lipid bilayers. While all or most of a lipid-soluble compound will be incorporated into the bilayers of these liposomes, the amount of water-soluble compound entrapped is usually very low because these MLVs have a small captured volume. Very little aqueous solute penetrates the onion-like layers of hydrated bilayer lipid. The captured volume of these MLVs can be increased by freezing and thawing the liposomes several times. Repeated freezing and thawing ruptures and reforms the MLVs, resulting in an increased number of liposomes with fewer layers of lipid and more aqueous space inside each liposome. Thus, the freeze-thawed liposomes encapsulate more aqueous solute and often have a multivesicular morphology. The aqueous solute is now uniformly distributed inside each liposome. The thin film method is limited to laboratory scale, while the reversed phase evaporation method can be used to produce milliliters up to thousands of liters of liposomes. Lipid is dissolved in organic solvent along with any lipid-soluble components. The aqueous compound is added to the lipid solution. This biphasic mixture is then emulsified by some form of high shear mixing. The organic solvent is evaporated from this emulsion, forcing the lipid into the aqueous phase, where it organizes into bilayers and forms liposomes. Additional aqueous phase is added in order to complete the liposome preparation. Again, the temperature of the aqueous phase must be above the phase transition temperature of the lipids in order for liposomes to form. Unlike MLVs produced from a thin film, liposomes produced by reversed phase evaporation usually have one up to a few bilayers per liposome. Like freeze-thawed liposomes, these liposomes can be multivesicular and have uniform aqueous solute distribution. Liposome characteristics can be optimized for a particular formulation by systematically varying the process parameters. Many variations of these methods are described in the scientific literature. Liposomes produced by these methods have a broad size distribution. The only method which can produce a definable unimodal distribution of liposomes in the 100 nanometer range is high-pressure extrusion through membrane-type filters of a fixed pore size. The stainless steel device, which supports the filters used for extrusion, withstands internal pressures in excess of 1000 psi. Extrusion cannot be accomplished with standard liquid filtration devices. Larger extruders are pressurized by nitrogen, while extruders handling volumes less than 1 milliliter utilize gas-tight syringes to generate pressure manually. Extrusion must be carried out above the phase transition of the lipids in the liposomes. In order to achieve a narrow size distribution, the liposomes must be passed through the filters 10 times or more. The liposome suspension becomes more translucent during extrusion, indicating that the liposomes are becoming smaller. The lower size limit of a liposome is 30 to 60 nanometers, depending on the type of lipid used. High shear methods are used to reduce multilamellar liposomes to unilamellar liposomes at their lowest size limit. Most water-soluble compounds must be present at the time the liposomes form to be encapsulated. Some ionizable compounds can cross the membrane in their neutral form and be converted to an insoluble salt form inside the liposome. This remote loading technique allows drugs to be loaded into liposomes after the liposomes are formed, but is not widely applicable. Some ionizable compounds can also be loaded into pre-made liposomes with a pH gradient. In this example, the neutral form, but not the charged form of a compound, can cross the membrane into the liposome, but can't escape due to the high concentration of protons inside the liposome. Lipids organize into bilayers due to the presence of water. When the water is removed by lyophilization, the bilayer loses its structural integrity. After rehydration, the liposomes have a different size distribution and have leaked their entrapped contents. Some aqueous solutes, such as sucrose, can replace water at the lipid head group, thus maintaining the bilayer structure when water is removed. In this case, the liposome can be lyophilized, then rehydrated while retaining its original size and entrapped contents. Membrane proteins can be studied in their native state by incorporating them into liposomes. The protein and lipid are co-dissolved in a detergent solution. When the detergent is slowly removed by dialysis, the protein incorporates into the newly formed lipid bilayer. For more information about liposomes, go to our website at www.incapsula.com.
So as you saw that this video not only covers how to make those kind of liposome nanoparticle, but also it also showed how to load those kind of drug molecules inside of those kind of liposome. One big difference between this liposome nanoparticle synthesis compared with those kind of metal or semiconductor nanoparticle is it started from a film. And then as we just break the film, it just become multiple different size of the nanoparticles. And then as we just keep filtering those kind of nanoparticles, we have a very narrow size distribution of the liposome. So using this way, we can make some kind of nanoparticles which can be used for the drug delivery or medical application. So this kind of stabilization of the colloid is kind of basically using this kind of self-assembled monolayer. So just coating the surface of the nanoparticle with this kind of organic molecules, we can just make the nanoparticles to be much more stable. And then actually this kind of, as we just talked about this self-assembled monolayer in the previous lectures, these molecules used for the molecular self-assembly is something like an rope-like structures. So we use one end as a ligand, which can attach to the materials like nanoparticles, and then the other end we can put any functional materials. So in this example, it attaches the protein which can react with some target molecules in the body. So using this way, this self-assembled monolayer not only make the nanoparticles to be stabilized, but also it can just modify those kind of nanoparticles to have a certain functions based on these molecules surrounding the surface of this kind of a nanoparticle. So let's talk about the vapor, liquid, solid approaches. So this approaches is normally used to make some kind of a nanowire formation. So this is the way. So the step one is we need some kind of catalyst material on substrate. So we can form this kind of a catalyst nanodot structures. If we want to have a very precisely positioned those kind of a nanodot, we can use a E-beam lithography and then do the lift-off process. Using that way, we can put this kind of nano metal catalyst with a very precise position and then very precise size. One easy way is we may just simply deposit very thin catalyst layer, in this case of that a gold layer. So as we discussed, as those kind of size of the material is kind of getting smaller, its melting point is also getting lower. So if we have a very thin gold layer, even though the melting point of the gold at bulk is about 1000 Celsius degree, we can make slightly melt this kind of a very thin gold layers around at 250 Celsius degree. And then once those kind of a thin gold metal layer is melt, it's just making just grouping and then just making this kind of a ball structures, nanoparticle structures, to reduce the surface energies. So using that way, we can achieve similar structures, but in this case of that, the size of the gold catalyst and then its distribution is kind of much more random. So once we get this kind of a small nano size gold nano catalyst on substrate, we apply source material. So in this case of that, we are growing silicon nanowire. So we apply either silane or chlorosilane. So when those kind of silicons just to see the gold, it just makes some kind of alloy in this catalyst. So this is the kind of phase diagram. So this is the gold and then silicon. So when we have this is the temperature. So when we have some kind of ratio of the gold and then silicon about this, actually at the very high temperature, those gold and silicon both are present as a liquid. But at this point, gold and silicon alloy present as a liquid, and then the silicon is present as a solid. So at this point, some temperature conditions around here with this kind of compositions, if we just keep apply those kind of source gases, what happens is these alloys still remain as a liquid, but underneath of the this catalyst alloys, those kind of silicons becomes solid, and then it just make this kind of becomes a silicon nanowire. So ideally, this is the kind of ideal scenario. So we have those kind of a gold catalyst. At certain point, we want to grow 1 nanowire, and then as we apply those kind of source gas, we just grow 1 single nanowire like this. So after finish that growth, we have still have the gold catalyst on top, and then this is the grown silicon nanowire. But in most of the cases, what we will have after the growth of the nanowire is kind of a much more complex, like this kind of hair ball-like structures. So those kind of grown silicon nanowires, or those kind of nanowires, intertwined each other, and then it just mixed like this. To improve this kind of a random positioning, people use this kind of a template. In this example, people use the alumina template, which has an kind of a very narrow kind of a distribution of the pore size. And in this case of that, people just putting this kind of a catalyst materials in the middle, and then during the CVD process, just growing this kind of a silicon nanowire. So using that way, people can avoid from this kind of a very messy growth. But as we just remove this kind of alumina template, those kind of grown nanowires also kind of present as a very kind of a complex mixed kind of paste. We can grow a carbon nanowire using the same kind of techniques. The major difference between silicon nanowire and then carbon nanowire is silicon nanowire, as those kind of nanowire is kind of growing, the catalyst material is kind of keep moving upward. As you can see from this cartoon, the carbon nanowire is kind of reverse. The catalyst is kind of stay on the substrate, and then those kind of grown silicon carbon nanowire, this one is a single walled nanotube, just to grow like this. So the position of the catalyst is fixed. So that's the major difference between silicon nanowire and then carbon nanowire growth. So for carbon nanowire growth, there are multiple different kind of catalysts that can be used. So all these kind of yellow colored element can be used as a catalyst. So when people just making nanowire based device, there are always kind of two stages. So the first stage is an nanowire growth, and then as you saw from this picture, most of the cases the grown nanowire is kind of very complex in structures, and then even the length and then the diameter of the grown nanowire is kind of different based on the size of the catalyst. So people just pick some of the wires out to the blank substrate, And then based on that isolated nanowire, people add some kind of electrode, and using that kind of ways, people can make the device out of this kind of nanowire. But this kind of a method is kind of not practical if you want to make a high throughput device fabrication. So what people are doing is, this is the pick and place. One is after growing those kind of nanowire, people just scratches those kind of nanowire grown substrate, and then just harvest this kind of grown nanowires, and then mixed with those kind of nanowire with some kind of a solution. And then as people just spin coating or whatever, applying this kind of a mixture of the solution of the nanowire onto a blank substrate, at some areas there is some kind of nanowires kind of pretty isolated. If then using the SEM, people just finding out those kind of a specific nanowire we can use as a device fabrication. And using the focused ion beam, we will talk about more details about these techniques later of the lectures, not today. We can deposit metal contacts on this kind of a grown nanowire, for example, silicon nanowire, and then these are the metal contact. So using this kind of a way, people can make the device. Or on that grown nanowire, using the AFM tip, people just take one nanowire and then just positioning that picked nanowire between the already formed electrode and then making the device. But this method and this method, both of them are not suitable for the mass production. So the next method is using the same kind of a solution mixed with the nanowire. People has an PDMS, that is a silicon rubber, and then it has this kind of a channel structures, and then simply flow those kind of a nanowire mixed solutions. And as those kind of nanowire just flow to one direction, those kind of nanowire tend to align to the directions of those kind of a flow. So in this kind of method, we can make group of wires just aligned to the one direction. If people want to have this kind of a direction and this kind of a direction, simply just rotate the PDMS mold and then do the silicon nanowire solution flow again. So using that way, people can make this one. But still, this method does not give a precise alignment of those kind of a single nanowire. Another method is using the electric field. Just apply the solution onto the already made electrode, and then applying the electric field, make this kind of a grown nanowires kind of positioned between the two electrodes. This example number 4 is much better way compared to the other 3 methods, but still it's kind of very hard to making the device out of this is not a good way to make the device in high throughput. So this is the kind of method. Actually, all those kind of, for example, I call that as a grow and place, because the growing and then placing is a 2 different kind of a step. But it is kind of a no control of the wires, number of the wires between the 2 electrodes. And then if we wanted to have this kind of structures with a one single nanostructure, it's kind of very hard to achieve that. So we talked about these approaches in the previous lecture. So this is the one of the example. We can do it much better. So this step and grow approaches use this kind of PDMS mold. So technically, this approaches merges those kind of growing and then positioning steps together. So after positioning this kind of a PDMS mold between the two electrodes, applying electrolyte which can grow the material. So as we apply the bias, we can just make the wires which can precisely positions between the two electrodes. So using that way, if we wanted to make the same structures over and over again under the bigger kind of substrate size, like an 8-inch or 12-inch, still we can make those kind of nanowire based device structures much more precisely. And then this is a much better way and then much suitable for high throughput production. But the thing is, as we grow this nanowire after growth, this one nanowire has a 3 interface, this, and then one interface with the substrate. So if the adhesion with this mold of the grown material is higher than the adhesion with the substrate, these kind of grown nanowires can be removed when we remove this kind of mold structure. So the first limitation of this method is those kind of material we want to have should be grown by the electrochemical deposition. The second term is those kind of adhesion of this material should be stronger with the substrate just compared with the adhesion with this kind of PDMS mold. So there are two conditions to be matched to use this kind of method. Another one is grow in place approaches. So that is another way. So using the way of making this kind of a template structure is the same as that stay and play, step and grow approaches. But this template used for the step and grow approach is a temporary mold. So using this kind of a small size of the mold, we can cover entire wafer. But this template in the grow in place approach is it is a permanent mold. So after one process, we cannot reuse this template again. So in this case of that, in wafer, we just make a bunch of gold nanowire. In this example, for the silicon nanowire growth, we just make a bunch of the silicon gold nanowire formation. So we may be able to use nano imprinting or E-beam to define the design of this kind of a gold nanowire. And then we can just remaining this kind of gold nanowire during the following lift up process. And then we deposit dielectric materials like silicon dioxide. So that is technically wrapping this kind of a silicon nanowire. And then opening both of the end. And then using the wet chemical etching, we can remove the most of the gold and then just the remaining very small amount of the gold slug in the middle. Then if we are using the VLS techniques, using this gold as a catalyst, we can grow silicon nanowire. In this case of that, this kind of a grown nanowire, its direction and then dimensions are very precise. So using this kind of a way, we can just achieve the silicon nanowire wherever we want to position. So this is the one of the example of the picture. So this is the gold nanowire after etching the gold. So this is the remaining gold. So the problem is since we are using a wet process to remove the gold, and then this channel size is a nano size. So at some point, those kind of a diffusion of the fresh etchant and then the diffuse out of the byproduct, chemical byproduct, is not good. So at some point, those kind of etch rates are getting getting lower and lower, and even depends on the channels. This kind of etching result is not uniform. And these all green channels are all empty channels. So once we achieve this kind of structures using the VLS technologies, we can just technically grow silicon nanowires. So once we just make this kind of a silicon nanowire growth, we can just oxidize the silicon nanowire. So those kind of silicon dioxide can be used on gate dielectrics. So as we putting this gate metal layers and then source and drain, we can just make an transistor structures. And this is the example of those kind of made transistor structure. So in these structures, it has an silicon. This is another kind of a way, but there is a silicon nanowire, and then drain and source is kind of positions here, and then here we have the gate dielectrics. So using this kind of a way, we made the transistor structure, which is an accumulated mode metal oxide semiconductor field effect transistors, and then it shows pretty good on and off current ratios, and then very small kind of sub-threshold swings performance. So just compared to the transistors made out of the top-down approaches, this kind of current on and off current ratios are almost the similar, and then this kind of sub-threshold swing is also very close or even better to the conventional transistor structure.
So how good its mobility can be?
The mobility-wise, actually, those kind of silicon nanowire, since those kind of size of the nanowire is kind of very small, like smaller than 100 nanometer in diameter, so that is why in most of the cases, those kind of silicon nanowire is single crystalline. And then another thing is we use the chemical vapor deposition technique, right? So that is why the grown nanowire itself is kind of material properties are very nice. So it is kind of almost as good as the single crystalline wafer. So that is why when we make the device out of this kind of approaches, we still have pretty good device performance. So today we talked about those kind of colloid and then colloidal chemistry, and then we also talked about those kind of vapor, liquid, solid approaches. And then we also reviewed some of the ways how we just positioning these kind of nanowires, and then what is the way people are use to make this kind of nanowire based device which is suitable for the mass production. So this is it for the today's lecture, and then see you next time.